are continuing our journey into organic functional groups and why they are important for life, and particularly biological molecules. So previously we examined our learning targets and we saw different ways to represent organic molecules. We've already looked at drawing and interpreting bond line structures. And for this series, we're going to look at reviewing all of our major organic functional groups. We're also going to examine the role of our functional groups in biological compounds. Now, previously, we've examined the basic structures of alkanes, alkenes, and alkynes. Now, the reason that these molecules exist, these are typically molecules that are found in nature, and they're found not what we call functionalized. They're not particularly useful to biological systems in the form of alkanes, alkenes, and alkynes. So they're the least useful to any sort of biological living system, and they require function in order to be useful to biological systems. So we say they require functionalization. So this is where the name functional group comes from, because it gives the molecule a purpose and a direction, particularly in biological systems. So here are a list of all of our functional groups that we've previously looked at and their importance. So a couple of the things to highlight here is the functional groups are grouped off and boxed off sort of by a generalized biological system usage or categorization based on their basic structure. So the first box in the upper left-hand corner examines ether and alcohol functional groups. These are what we just call the simple O functional groups, because in the case of the ether, we have just the oxygen bonded to a carbon on either side. Now that's the characteristic definition of an ether. Here, the functional R1 and R2 simply represent arbitrary carbon chains that can be attached. That means any number of carbon chains can be attached. But the characteristic understanding of an ether is that there is a carbon that's bound to either side of an oxygen, on either side of an oxygen. Whatever else is bound to the carbon is not so relevant, but just that you have a C-O-C-C bond. In the case of an alcohol group, this characteristic is also commonly called a hydroxyl group. What's characteristic of it is that you have an OH here, and sometimes this OH is drawn this way, where the O is shown as a line structure with the H. That's a common occurrence. And this O must be attached to another carbon structure. So the COH segment is required for a hydroxyl group. Now, please note that a hydroxyl group is not a component of any of the other functional groups. This is often confused, point of confusion among students, that, for example, the carboxylic acid, it has an OH here, but that does not mean it is a combined functional group. Functional groups are not combinable. They don't have segments, like one belongs to this group and then the same within the same group is there belongs to another group. So OH is only found as the O and H by itself attached to another carbon. Okay. Looking at our second box on the lower left, we have the aldehyde. So the aldehyde is characterized by the characteristic C double bond OH segment here. This typically occurs only at the terminal end of a chain, because there must be a hydrogen on the structure. It cannot have anything else but a hydrogen. And on the other side, we're characterized by attachment to a carbon. So often you will see CHO. It's written often this way as a CHO to distinguish it from an aligned structure, to distinguish it from the alcohol functional group. So we know that that means C double bond OH, and the only other characteristic is that it's attached to some other carbon structure on the other side. Whereas the ketone, on the other hand, the ketone simply is characteristic by the C double bond O attached to two other carbons. Now, the single C double bond O species by itself is referred to as what we call a carbonyl. Now that's any C double bond O. We refer to it as a carbonyl structure. So the functional groups in the box on the left and the box on the right here, these are often called the carbonyl functional groups, okay, because of the characteristic C double bond O that is required in the presence of these groups. On the upper right-hand corner, we have the amine functional group. This is simply a nitrogen that's attached to a carbon. It's very similar to the alcohol functional group, except that instead of an OH, you have an NH2. Please remember that it must be an NH2 because nitrogen has to have 3 bonds. Looking at the box in the lower right-hand corner, the first group that we have is the ester. Now, please notice again here, this is another phenomenon where this whole piece here is required for the ester. The ester is not a composition of the carbonyl plus an ether. It is not that. To have an ester functional group, you must have the C double bond O attached to an O, which is attached to another carbon group. So this is a characteristic, and it cannot be broken apart into segments or pieces to say that it's a ketone plus an ether. It is not the case. It is an ester. It must come as a whole unit or it doesn't come at all. The same idea with the carboxylic acid group, or sometimes called the carboxylate group. And it is often called the carboxylate group because you will often see it as a charged species, a charged atom, which it looks like this, C double bond O with a minus charge. That's also related to the carboxylic acid. So this group here comes as a unit whole. It cannot be separated. It is not an alcohol combined with a carbonyl. That is what it's not. It comes as a whole unit. And the last piece is the amide, which appears again to be an amine plus a carbonyl. It is not. It comes as a whole unit. Okay. Now, in this case, this does not. The R groups here are any sort of carbon chain of any length that we have. Okay. So these are our major functional groups. Now, where do we find these major functional groups in biological systems? So here, let's look and examine alcohols and ethers. Now, in biological systems, there are 4 major molecular groups that we have. Okay. The first major group are called carbohydrates, which are these simple sugars. Carbohydrates are also sugars. So here we have on the left side a complex sugar. This is sucrose. This is what you know as table sugar. And it is a combination of a 5-membered sugar and a 6-membered ring sugar. And as you can see, there are only OHs and ethers. There's our ether. There's our other ether as part of a ring. Here is an ether bond. This is often called a disaccharide linkage. In biology. So this is an ether linkage here. This is also an ether here. And all of these other functional groups here are all hydroxide. So complex sugars as well as simple sugars, if you take a look, one of the simplest sugars, glucose, you have again only ethers and alcohols in this form. Now there are other forms of sugars that can be drawn differently that show the presence of aldehydes and ketones also, but I've chosen to draw them in this form so that you can see the utility of the ether and alcohol functional group. Here is a simple molecule, one of the simplest sugars that we find in the body. This is called glycerol. Glycerol is also a composite component of fats because of the three OHs here. But these, again, OHs are very important functional groups in biological systems, particularly in sugars, both simple and complex. Next, we look at the ester, carboxylic acid, and amide. Now, at the top is one of the more important small molecules that are important for biological systems. This is called an amino acid. It's referred to as an amino acid because there are 2 major functional groups that you have here. Here is the amine functional group on the amino acid. And on this side, you have the acid, the carboxylic acid functional group. So this amino acid is exceptionally important in biological systems because it is the building block of molecules that we are going to call peptides, because the bond that we're going to refer to in biology is often called the peptide bond, which is this bond right here. It's referred to as a peptide bond. It's where the amine bonds to a carboxylic acid and produces water as a byproduct, producing what's called a peptide bond. So that peptide bond is the major bond that holds protein molecules together. So proteins are polymeric structures that are composed of these smaller amino acid units that we find here. So we take two amino acids and we string them together, and we get what's called a dipeptide. So here, if we slice this down here, there'll be two simple amino acids that we brought together to make a dipeptide. Okay. The other type of molecule that we have where the carboxylic acid is also an important functional group is here. This is a fatty acid. This is docosahexaenoic acid, and this is DHA, which is very important in brain building and brain development for babies and pregnant mothers to have in their diet. So this is a long chain alkene, as you can see here, alkene unsaturated system. Okay, because you have unsaturated bonds, and here you have completely saturated tail segment. But this is the basic building block of a fat. So you have these long carbon chains that are attached by an acid group here, and this acid functionality will eventually bond to glycerol. Here's the glycerol molecule that I showed you before, without the H's, right in there, and then these smaller groups out here that I'm going to put in the box, okay, these belong to the fatty acid group. So here are how the ester and the carboxylic acid and the alcohol all combine together to sort of make this new simple fat structure. So these functional groups, they're not just in isolation, they're really important in the making of biological molecules inside your body. So let's pause for a second and do some practice with identifying our functional groups. Here is a molecule called Taxol. Taxol is used for chemotherapy for treatment of breast and ovarian and non-small lung cell carcinoma, or a type of lung cancer. So pause the video here and take a few minutes to try to identify all the functional groups that you can in this molecule. And you can begin to replay the video when you've completed, where I'll go over all of the functional groups that are present. So let's start with the functional groups on the far left of this molecule. So here we see this functional group over here. And this has the characteristic carbonyl plus amine. So together, carbonyl here, this whole group comes as a unit. This is an amide. Okay. Here we have just the OH by itself, so this is an alcohol. Here we have C double bond O and O by itself. So this will get the term ester. Because remember, we can't separate them in any sort of way. So up here at the top, again, there's a nice another ester. Here's another alcohol. Just going to draw that a line over there. And again over here in this box that I'm going to put over here, and over here also, these are two esters again. And over here you have an ether. Here is an alcohol. Whoops. And here is a ketone. Because in this case, there's carbon on either side. There's no hydrogens on either side. So that is a ketone. So present in this Taxol molecule are an amide, a number of esters. We got 1, 2, 3, 4 esters, 1, 2 alcohols, an ether, and a ketone. And that's it for this video.